All right, today we are jumping straight into the LongCat-Image technical report. This is a really important paper from the Meadow and LongCat team.
It really is, because it basically challenges this dominant idea in the industry right now.
That bigger is always better.
Exactly. This idea that you have to just keep scaling up.
So for those of you with just a minute, here's the quick rundown on LongCat-Image.
Okay, first, the core takeaway is all about efficiency and specialization. This model gets state-of-the-art results with a really compact core. We're talking just 6 billion parameters.
Which is tiny compared to the 20 billion parameter models or, the huge mixture of experts architectures out there.
Right. Second, they got this incredible photorealism by being, incredibly strict with their data. They filtered out all AI-generated content during training.
And then they used an AIGC detector as a reward signal during the alignment phase, which is a really clever move.
A very clever move.
So?
Third, and this is a big one, they just nailed Chinese text rendering. This has been a huge problem for years.
And their numbers are staggering.
A
90.7% overall score on the Chinese word benchmark. I mean, that just blows the competition away.
It's industry leading, no question. Fourth, the image editing is top tier for open source models. It's got fantastic visual consistency and it follows instructions really well.
And finally, they're opening it all up.
Yeah.
The final model, those super useful mid-training checkpoints, the developer version, and the whole training tool chain.
Which really lowers the barrier for researchers everywhere.
Okay, let's unpack that core design philosophy, this idea of efficiency over just brute force scaling. It really flies in the face of what we're seeing.
It does. I mean, they looked at the trend of models getting bigger and bigger, QuickImage at 20B, Hunyuan 3.0 with an 80B MoE, and they basically said, wait a minute.
The gains aren't proportional to the cost.
Exactly. The qualitative leap just isn't there. Instead, you get these soaring computational costs, massive deployment barriers, and just awful inference latency.
Yeah, if you're an MLOps, you know that pain. It makes real-time applications almost impossible. So they landed on 6 billion parameters as this sort of ideal foundation.
It's their sweet spot for balancing capability and efficiency.
So what does the architecture actually look like at that size?
Well, the core diffusion model is a hybrid structure. It's influenced by flux1.dev, so it's a mix of a multimodal diffusion transformer, or MM-DiT, in the early layers.
Okay.
And then it transitions to a simpler single DiT structure for the later layers. They kept the attention block ratio at about 1:2, double stream to single stream to keep things efficient.
Now, for the text encoder, they used Qwen 2.5 VL7B, which is a powerful model in its own right. It's 7 billion parameters.
Right.
Doesn't that kind of undercut their whole 6B efficiency argument?
That's a great question, but I'd say it's more of a necessary dependency. The 6 billion refers to the core generative part. You still need a really powerful unified encoder to feed it that rich conditional information.
Especially for something as complex as Chinese.
Exactly. You leverage a known high-quality knowledge base for the conditioning, and you optimize the heck out of your generator. It's a smart trade-off.
I was also really struck by their approach to positional embedding. They didn't use any of the complex heuristics we see in other new models. They just went vanilla.
Yeah, it's fascinating, right? Most new systems have these intricate tricks, coordinate centering, frequency scaling, just to handle different aspect ratios. LongCat just used the standard 3D multimodal rotary position embedding, the MROP, with no tweaks.
But isn't that a huge risk to just rely on the model's intrinsic adaptability instead of engineering a solution?
It seems like a gamble, but their results suggest that if your core architecture is solid and your data is clean, the model just learns. It figures out how to adapt its positional strides on its own.
And the upside is a much simpler model.
Much simpler. It means faster training, easier deployment. You're not dealing with all these complex post-processing layers. They show it works across tons of aspect ratios and resolutions. The complexity just wasn't needed.
Okay, so that brings us perfectly to the data. Because to make a 6B model compete with an 80B model, the data strategy had to be bulletproof.
It had to be. And their key finding here was that even a tiny amount of AIGC data in your training set can be poisonous.
How so?
It causes the model to converge way too early into this narrow local optimum. And that's when you get that telltale look, that sort of plastic, or as they call it, greasy texture that just screams synthetic.
So how do they clean it all out? What did the pipeline look like?
It was rigorous, a three-pronged filter, really. First, they used a specialized internal AIGC detector to just exclude all of that content, period.
Wow.
Second, they set a high-quality bar. Anything below an LA on aesthetic score of 4.5 was just thrown out. And third, they used a two-tier deduplication with both MD5 hashing and siglet-based similarity to make sure there were no near duplicates.
That is an incredible amount of work.
But it pays off in the final image fidelity. Then they structured the training itself.
The progressive mixed resolution training.
Yep. Started at a tiny 256 pixels, moved to an intermediate 512, and then finished in a dynamic range between 512 and 1024. But the crucial part during this pre-training was that artistic or stylized data was kept to almost nothing, like 0.5% of the total.
So they were building a purely photorealistic foundation first.
A very strict photorealistic foundation. Then came the mid-training stage.
And this is where we get that developer version checkpoint that everyone's excited about.
Right. This is where they did quality enhancement and started injecting some artistic style. They brought in high-res images and let the stylized data creep up a little to maybe 2.5%. The model that comes out of this stage, the developer version, is prized for its high plasticity.
We should probably define plasticity here for everyone. Why is that what you want in a mid-training model?
Well, when a model goes through its full alignment, especially reinforcement learning, it gets really, really good at what it's been trained on. It becomes optimized, but also rigid.
Right. Hard to teach it new things.
Exactly. Plasticity means it hasn't been locked into that narrow state. It's still incredibly flexible and receptive to downstream fine-tuning. It's the perfect starting point if you want to adapt the model for your own specific tasks.
And this whole photorealism obsession carried through all the way to the final RL alignment.
It did. They took that AIGC detection model and, in a really clever twist, they used it as one of the reward models.
So it's an adversarial signal.
It's a perfect adversarial signal. It actively punishes the generator for making anything that looks synthetic, and it pushes the output toward the texture and detail of the real world.
Okay, let's switch gears to where they truly just left everyone else behind. Chinese text rendering.
This is such a massive headache for generative models.
Yeah.
The sheer number and complexity of Chinese characters, especially the rare ones, it's a huge challenge.
And LongCat-Image now has industry-leading coverage.
The numbers are just wild. On the Chinese word benchmark, they hit 90.7% overall. To give you some context, a top competitor like Seadream 4.0 is at about 58.5%.
That's not even close. It's a game changer.
It is.
So how did they manage to get that level of textual accuracy without just flooding the model with, text-based images and ruining the photorealism?
They used a lot of synthetic data, but they were very smart about it. They use a tool called SynthDog to generate over 10 million text samples.
10 million.
10 million, but they were rendered on very simple backgrounds like blackboards or paper with a ton of typographic diversity. This forced the model to learn the character shapes, the glyphs, without being distracted by complex backgrounds.
But wait, that sounds like exactly the kind of thing that could damage the model's realism. How did they stop it from just learning to make images of text on blackboards?
They used a brilliant strategy called dynamic sampling. They were monitoring the accuracy for each character in real time. If the model was struggling with a certain character, they'd automatically increase the sampling probability for its synthetic data.
To force it to practice.
But as soon as the character was well learned, they dial back the synthetic exposure and show it more real images. This feedback loop stopped it from overfitting to that simple synthetic world.
That's incredibly clever. And they also made a key architectural change to the text encoder itself.
A small but critical one. Instead of using a huge specialized text encoder, they just modified their standard one. They applied a character-level tokenizer, but only for the text inside quotation marks in the prompt.
So it isolates the text rendering task.
Exactly. It makes the learning for glyphs way more efficient without the massive memory overhead of a whole new encoder. It's perfectly in line with their whole efficiency-first philosophy.
Let's move on to editing. This is always the acid test for a model's stability.
It really is. You need two things: precise instruction following and just rock-solid visual consistency in the parts you didn't edit.
And that's the hard part.
It's the hardest part. And they realized that the final post-RL models were too rigid for this. They had lost that plasticity, so they made a really counterintuitive choice.
They initialized the editing model from the mid-training tech point.
From the developer version. They chose the less refined model specifically because it had superior plasticity and could generalize better to all the weird and wonderful things people do with editing.
So flexibility was more important than pure generation fidelity for this specific task.
That's it. Optimization for text to image can actually hurt you when it comes to complex multi-step editing. So during the editor training, they used multitask joint training.
Mixing editing tasks with standard generation tasks.
Yeah, to prevent catastrophic forgetting. You have to keep reminding the model of its core generative knowledge. Otherwise, the image quality falls apart while it's learning to edit.
And this brings up the big caveat they mentioned, why the T2I and editing models are still separate.
Right. They were very upfront about this. It's a data problem, not an architecture problem. They found that the heavy reliance on synthetic data for editing training, which is pretty standard, was degrading the photorealism of the base model.
So to get the absolute best quality for both, they had to keep them separate for now.
For now, yeah. But despite that, the editing model is state-of-the-art for open source. It handles multi-turn editing, where you make several changes to one image really well.
And compound instructions, multiple edits in one prompt.
It nails them. And the human-centric stuff, like adjusting a portrait or changing a pose, is very impressive. It maintains consistency without the background or the person's features just, falling apart.
So let's get into the final line on techniques. After the supervised fine-tuning, they used 3 different RL strategies.
Right. SFT was for refining high-frequency details. Then came the RL, which was guided by a whole suite of reward models, OCR, accuracy, distortion, that AIGC detector again, and of course, human preference.
They started with direct preference optimization, or DPO. How did they build that data set? Signal quality is everything there.
It was meticulous. For each prompt, they'd generate 6 candidate images. Then, human annotators would mark the best ones, a score of 4 or 5 as positive, and the worst ones, a score of 1 or 2 as negative.
Which creates very clear win-lose pairs for the algorithm.
Exactly. Generating 6 options gives you a rich set of comparisons, so the DPO gets a really high confidence signal to learn from.
But the real innovation here, the really technical part, is their monolithic policy optimization, or MPO. What problem does that solve?
MPO is their novel on-policy method, and it's all about training efficiency. Previous methods like GRPO, Group Relative Policy Optimization, have these synchronization bottlenecks between different parts of the optimization process.
Right.
MPO gets rid of that. It moves to a single-stream monolithic optimization, which is just much more stable and efficient for these huge distributed training runs.
And it has 3 key technical components that make it work.
It does. First is a Gaussian value tracker. You can think of this as a kind of running scorecard for the model's expected reward on any given prompt. It provides a stable baseline.
And what stops the model from just drifting wildly away from that baseline?
That's the second component. KL adaptive forgetting. This is a mechanism that kind of dynamically adjusts the learning rate. If the policy starts drifting too far, if the tracker sees high variance, it scales up the process noise to stabilize learning and prevent these huge catastrophic jumps.
And the third piece is about making the sampling more efficient, I take it.
Precisely. It's called the uncertainty-powered curriculum. It's a scheduler that makes the model focus on what it doesn't know. It looks at the variance from that Gaussian value tracker and prioritizes sampling prompts where the model is most uncertain about the outcome.
So it's always working on the hardest problems.
Which is the most efficient way to learn. It maximizes the impact of every single training step.
All of this, the training, the architecture, it just reinforces their main theme. Deep specialization and efficiency are king. And their open source contribution really reflects that.
It's an exceptional commitment. They didn't just dump the final model. They released that super plastic mid-training developer version, which for many researchers is even more valuable, and the entire code base for training and fine-tuning.
That dramatically lowers the barrier to entry for other teams.
It really does.
And human evaluations confirmed it. They're at the top of the open source pack in both quality and consistency, even if they admit there's still a gap to the very top closed-source commercial systems.
Right, and that gap sets up their final point perfectly. They've proved that a specialized, compact model can be state-of-the-art in key areas like bilingual text and editing consistency.
And they were clear that separating the generation and editing models wasn't an architecture choice, it was a data choice. The synthetic editing data was hurting photorealism.
And that's the open frontier they point to, solving that data mismatch. They think the future is using massive interleaved corpora.
Image text sequences mined directly from the web in order.
Exactly, to build these huge, high-quality, real-world editing data sets so you don't need to rely on synthetic data anymore.
So the challenge isn't just more parameters, it's about building better data pipelines to finally unify generation and editing without compromise. The question for all of us is, how quickly can the industry make that transition? When do we finally get that single unified model that doesn't suffer from this data mismatch and rigidity? Because that seems to be where the next big breakthrough is waiting.